So, we're going to talk about the fundamental forces here for about 10 minutes. And after those 10 minutes, we're going to call it good. Then we're going to talk about what mass is and weight is, because, we haven't been talking about those for, a few months. And then we'll get to the lack thereof, which is the most interesting part of this. All right, so here we go. We're going to talk about the 4 fundamental forces. We watched that quick video a few days ago. If you don't remember it, I did link to it on Canvas, so you can look there. And if you want more information, I did also link an article that you can take a look at to talk about these forces. So the game is, do you remember a long time ago I gave you that chart that had all those forces on it, and we were organizing our forces? Yep. Yeah, most of that's a lie. Today is the truth-telling time. There are really only 4 forces that make up everything in our universe as we understand it today. And I'm going to couch everything in that, because 20 years from now, as physicists, we may have discovered some brand new thing that pulls it all together. And I don't want you to come back and shake your fist at me and say, Miss K, you lied. I'm telling you, this is what we know as of today. You all may be the ones that figure it out, and then, that's all cool. But we're going to start with what we know today. Let's start with electromagnetic. We'll kind of go through each one of them, and we'll kind of bounce. I think we'll do attractive and repulsive for everything here real quick. Maybe we'll just kind of see. We have not yet talked about the electromagnetic force, but on Friday, I think, we're going to get to know electricity very well. But today, what do you know about the electromagnetic force? Is it attractive or repulsive? Both. Or both. It is. Yeah, you've known that in your life for a long, long time, right? You got to play with magnets when you were in preschool, and you got to see that they were attractive and repulsive, and magnetic is part of magnet, and so there you go. All right. The type of particles that interact that are impacted, in terms of the electromagnetic force are what? Does anybody know? Charged particles. They have to be charged, yes. So what kind of particles do you know that are charged? You know protons, right? And you know electrons. And after the AP test, we'll get into this a little bit deeper, but FYI, protons aren't really particles. They're really combinations of particles. Okay, just FYI, okay? Those particles are called quarks. No, Q-U-A-R-K, quark. Okay? Now, these charged particles, these quarks and electrons, and there are a few others too, but we're not getting into that today. After the AP test, we'll dig in. It'll be interesting. But for now, we're just going to talk about those because those are the ones that we kind of know about. Those are the ones that are impacted. But the fun thing about these 4 fundamental forces, none of them are contact forces. They're all field forces. And the interesting piece there is that a field force, according to physics and according to physicists, is really just an exchange of these other special kinds of particles. And the special kind of carrier particle that exists, that causes electromagnetic force to exist is, anybody know? Anybody know? It is a photon, a particle of light. Okay? In my other physics classes right now, we are literally talking about light, and we just talked about how when charged particles move, you get light. That's exactly like we're doing the opposite of that in the other class today. How strong is the electromagnetic force? Strong. It is the second strongest of all of the forces. It's the second strongest, and we'll talk about the relative strength once we've got them all in there, because otherwise it doesn't mean anything. Okay? The range of the force, how far out does that force go between 2 charged particles? Pretty far as we can imagine. It goes out to infinity. Yep. Okay? Electromagnetic forces. What kind of forces are electromagnetic forces? Magnets. That's a good one. Electricity. You guys are so cool. Those are the 2 easy ones. Any other force that we've talked about this year except gravity? The normal force? That's an electric force, but the friction is also an electromagnetic force. Any of the contact forces are really, pull that curtain back, they're really all just electromagnetic forces. If I asked you to draw a free body diagram of me as I stand here, now I don't want you to do this on an AP test because that's not where they're going with this, but I just want you to know this, right? The two forces that you're going to tell me, if I asked you this before I had this conversation with you, one would be gravity. The force of the earth pulling down, that's gravity. And the other one is what?
Normal force.
The normal force. The normal force is really, literally, the two surfaces pushing off of each other. Now, we all know, because most of you have taken chemistry, that each of those pieces of that material are made up of atoms, right? And an atom is made up of protons and neutrons in the middle, right? In the nucleus. And then you've got electrons that are orbiting outside. So you've got electrons on the very, very, very surface of the floor. And I've got electrons on the very, very, very surface of my shoe. And I've got negative charge and I've got negative charge. And do they want to be together?
No.
Nope. And that's why you don't fall through the floor.
Wait.
True. No. Hold on, friends. Oh my gosh, we gotta go fast.
I'll talk to you after class.
Okay. Like it's kind of like a brain explosion kind of situation. Or are we okay?
Yeah.
Okay. All right. Strong nuclear. The strong nuclear force is strong. Yes. In fact, we'll put the strength of force. It is indeed the strongest of the forces.
Why is the weak nuclear force stronger than the strong nuclear force?
Because that would be dumb. Let's not do that. All right. Really quickly, most of this detail is not stuff that you need for the AP exam, but I feel compelled to give it to you because I think it's important. The strong nuclear force is primarily an attractive force. Okay? It's primarily an attractive force. Some people would argue that there's some repulsive stuff, but we're going to just talk about the attractive because that's the part that makes the most sense. But it's attractive only at very, 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 very short ranges. Okay? It only acts at distances of less than 10 to the negative 15th meters. Right? Whoa is the right answer. What is that small? The nuclei, right? Okay, I have a question for you. What's in a nucleus?
Protons
and neutrons. Now, I don't know if this has ever crossed your mind, because until somebody pointed that out to me, it never crossed my mind. You have protons, and what kind of a charge do they have?
Positive.
And you have neutrons, and what kind of charge do they have? Do the protons want to be near each other?
No.
They got the
If you have two protons together, and helium has two protons together in very close proximity, according to electricity, do those two protons want to be near each other? No! So if electricity was the only thing that mattered, we would not be here. Like, matter would not be here. Are you with me? Do you understand what I'm saying here? Protons don't want to be near each other because they're all positive charges. Neutrons can't do anything about it because they're neutral. And so all you've got is this bunch of positives. The positives don't want to be near each other. If we don't have this thing, we got nothing. Okay? The strong nuclear force is the force that holds what they call nucleons. Nucleons are the protons and the neutrons. What holds them together? Okay? The strong nuclear force impacts or acts with nuclear particles. Okay? By that I mean neutrons and protons. And really by that I mean quarks. Okay? The carrier particle, the thing that keeps all of these things together, that sticks them all together, they're called gluons. Gluons. That's what they're called. Okay? The example, the thing that we want to write down here is that they hold the nucleus together, right? That's like literally what it does. Holds the nucleus together. You know how you look at the periodic table and there are a certain number of elements that are stable, right? And then beyond a certain size, the nuclei just aren't stable anymore, right? So you can only maybe get it to exist in the lab for a split second. The reason for that is because the nucleus is too darn big. Once it gets bigger than this, those protons say, see ya, we don't want to hang out together, we don't want to stick together, and then they don't. Then they're not stable. The strong nuclear force is the thing that holds them together. Okay? The weak nuclear force. Now, we're going to use our power of understanding here. Okay? How does the weak nuclear force compare in strength to the strong nuclear force? It's weaker. Now, I kind of gave you a hint here because I told you that electromagnetic happens to actually be the second strongest. The weak nuclear force is going to be less strong than that, obviously. Yeah. So it's going to be the third strongest. Yeah. Yeah. Which still is kind of a misnomer given that it's called the weak nuclear force and it's not the weakest, but it's the least weak or the least strong of these forces that fit the standard model that make everybody happy. This is the one that gets everybody crabby. Okay. Unless you really like gravity and then, whatever, you do your thing. All right. The weak nuclear force is also a fairly attractive force. Okay, but I would say that you could argue both. Okay, but I kind of write it that way. At short ranges is what I usually write. Okay. The weak nuclear force also interacts with which particles? The nuclear particles. You can call them nuclear, right? Yeah, nuclear. Yeah, the nuclear particles. Don't do it the other way. It just is not good. It makes you not sound smart. You can also call them nucleons. Nucleons are the protons and the neutrons. And the way that the weak nuclear force works is, I'm just going to say nuclear particles in decay. We'll talk about the decay later. I just don't want to get into it today because I don't want to spend too much time. The names, there are 3 carrier particles. There are a number of different gluons that we're not going to get into. But the weak nuclear force has 3 bosons. I know, right? You just love this. It's great. There's good stuff. They're called W plus, W minus, or excuse me, W plus. Is it W minus or W zero? W minus, I think.
Is the 3 part of the name or is it just?
No, there are 3 of them. 3 types of them.
My bad.
No, the Higgs is not one of them.
Where's that one?
The Higgs has to do with mass. We'll get there some other day, after the AP test.
Oh yeah, we're just gonna do fun physics.
We don't have 3 anymore.
We got to get there first. We got to get through this stuff
do
first.
really cool labs like dropping one.
No. All right, we got to go, friends. Oh my gosh. Shh. The range of this force is actually smaller than that of the strong nuclear force. It's less than 10 to the negative 18th. Pretty small. And the weak nuclear force is what is responsible for all radioactive decay. Oops.
Godzilla's made of.
So it's funny because all of the stuff that we've talked about so far today is new, brand new stuff that you've been experiencing all your life, but you've never really embraced in a physics sense. Whereas this last one, you've known it and loved it for a long time, right? Let's talk about it here real quick. Gravity is only attractive all right. Okay, friends. Gravity is only attractive. The weak nuclear force again and the strong nuclear force are attractive at short ranges, and then they are what do I say? Repulsive at longer ranges. So we call it both. Gravity is only attractive, and gravity deals with what kind of particles?
Everything with mass.
Everything with mass. It's got to have mass. Antimatter also has mass. Yeah. We'll talk about that another day, not today. Yeah, you can make antihydrogen with an antiproton and an anti-electron. It's also known as positron. Yeah, it happens. Part of the reason that we don't really understand gravity is because the carrier particle, unlike all of these carrier particles, is one that we have not yet found. We have not yet detected it, which makes it really hard to, make sure that we really agree with. Okay, does gravity really exist? I think it does, but we don't understand how it exists because we have this thing the elusive thing that we've never found. It's called the graviton. Okay.
You can't see it. It doesn't exist.
How what?
Maybe not. Well, the Earth is.
I'm going to say no.
You want to measure the distance between your foot and your.
All right. The strength of the gravitational force, kind of by definition, it's got to be the weakest of all the forces. But now, just to give you a little bit of a sense, oh no, I wrote this down wrong. Oh, stink. Hold on just a second.
Yeah, you should get fourth strongest. At least it has.
Please.
Do you need this? Just take it. Have a great day, you guys.
Why would I know that? Like, that's not that. There is, but it's relevant to me. I'm not relevant to myself. Okay.
The Earth is moving 3.8 something square on the back of the giant tortoise.
This is the outside donut, guys. Okay. The center of the Earth. The moon is the donut. Think about it, guys. The Earth is a donut. What about hollow ground on the inside of it? The moon. What about this thing? What about, you know how we have an ocean, right? What if just one big ocean? And it just doesn't end. It just goes like that. So the moon got
Bro,
No, I didn't.
that actually makes so much sense. That our Earth is